Brad? All right, that was the recording in progress. I'm going to tell the computer that I got it, that I'm being recorded. So some might ask, why do we record these things? And the number one reason in mind is that we have no idea really how big the audience is on YouTube. So I strongly encourage you to delve in the archives of our YouTube channel and have a look and see what there is to see out there. I wanted to mention the Mountain View Press archive. Speaking of archives, all of these books that are being slowly leveled into the recycling apparatus. The storage for that runs, I think it's $185 a month. If you're interested in participating in that, please contact me, either through Meetup or through my email address. Try to get this right this time. I'm going to post it on the chat when I stop blathering. But it's forther@comcast.net. That use .com there are going to be sad at not reaching me. I think there's another guy that is forther@comcast.com, and he knows who I am. I know who he is, and he'll point you at me if you screw up. But let's not make an issue of that. So any piece of that you care to my way, I guess you're just enabling me. If we get tired of hemorrhaging money, we'll pick up the pace at recycling the paper. If any of you are interested in old copies of brand new copies, as it turns out, of Fourth Dimensions, probably you're better off looking at the scans on the website. But Asilomar and Rochester are both well represented, and other works. Anyway, if you're interested in any of that stuff, please contact me. I'm pleased to consider sending it to you. Klaus has his hand up.
Yes, Kevin, is it possible to have the video recording of my presentation from last month, because I would like to include this in my Git presentation.
Other than on YouTube?
I haven't seen it.
Brad, is it on YouTube?
It is. In fact, I was just quoting the numbers into the chat. Coincidentally, around there were 192 viewers, so that sort of justifies why we record these. Let me go back and I'll paste the link to it in the chat.
I think 192 is a spectacularly wonderful number.
Even more impressive is the number we got for the Factor Talk, 1.6K.
Well, that's trendier, you know.
Yes.
We're fourth enthusiasts. We're less enthused about trends and more enthused about stuff. All right. So that's enough blather for me. Thank you for being here. Welcome to the April SVFIG Zoom meeting, the direct lineal descendant of our monthly meetings at Stanford. I'm Kevin Appert. I'm the program chairman, and other furniture as required. I'm pleased to introduce Klaus with his part 2 of his microCore stuff, but it's not my role because here we all introduce ourselves. So Klaus, introduce yourself, and let's get on with the show.
Oh, it's me. Okay. So I'm Klaus Schleisiek, and I learned about force when I met Bill at the very first West Coast Computer Fair, or San Francisco Computer Fair it was at the time. And he handed me over the 6502 booklet about FIG and so on. Since then, I have been using force, and later on, I even participated in the Force 83 standardization effort, which was an interesting thing for me coming from Germany and having never heard about Robert's Book of Rules. So at some points in the meeting, that was very important, up to the point that a struggle occurred about which issue would be the valid one for this meeting. So I have been using force since then. When I came back to Germany, I thought I have good employment opportunities, mastering a technology which was far ahead of what was customary at the time in Germany. And that turned out to be not true, because nobody had heard about it. Nobody was looking for me. And so I wound up to be self-employed, and for the rest of my life, I built scientific instruments based on force, and since 2005 also on microCore. Anyway, I now share my screen with, where is the screen sharing? Share screen. This is complicated. Just a second. Okay. Oops. I hope you all see now a microCore VHDL code and structure, right?
Yes. Yes, we see it.
Okay, so here we go. Just as a reminder, this is the design flow of the microCore environment, and the red outlined boxes are, let's call it, source code, and all the other things are derived from that source code. And today will be speaking about the microCore application interfaces, microCore and application interfaces. That's not true. We are talking about microCore, and not about force code for the moment, and architecture. So there is an architecture description of the of microCore that is both interpreted by microCore itself and by the force cross compiler. And just to give you an impression, the architecture file, I will go through this in a short while. This is the wrong file. This is it. Here you see this strange -- VHDL. Now, -- VHDL is a force word. And as far as VHDL is concerned, VHDL just sees the -- and treats the remaining line as comment. So this is a mechanism how force can handle this text. And here is the actual code of the VHDL interpreter. And as you can see, this is very simple. This is a very simple thing, because all it has to do And I go back. I mean, I don't want to get into this code, just to show it to you of how simple it is. What it has to do, it has to import like these constants and other constants later on, because they need to be known in the force environment as well as in the microcore environment. And so like, for instance, the data width is 32 bits. And when force loads it, it also creates a constant named data width with a value 32. And with this technique, the hardware and the software will never be out of sync. They are automatically always in sync. And even if I throw away instructions from the VHDL code and and if I then load the force code, and then if I use this instruction which I have used, which I had defined before and erased from the VHDL description, then force is going to bark at me and say, what? I don't know this. And so it is guaranteed that it is always in step. Okay. This much as an introduction. I now go through the architecture file because this is really the important thing of the whole of everything. So we have a couple of constants, simulation. Well, why do I have a Boolean constant simulation? Very simple. In the real code, like for instance, for the timer that times out every 250 microseconds or so, for simulation, this is rather bad. And so while I'm simulating, I can load the timer with different starting values or with different divisors. So I can make the ticks happen much more often to see it very quickly in simulation. Then there is a constant cold boot, which means when I do a reset of microcore, I have two choices. I either just jump to the reset vector and start again from there, or I jump to the cold bootloader, which is firmly synthesized into microcore. And this also is derived from a program. And so cold boot, if it says set to false, then I just start at the reset vector. And if it is set to true, then the cold bootloader is invoked again, and I fill the program memory, which is RAM for speed reasons, and I reinitialize the program memory. Extended means it is either an extended or the core word set. With mult means if there is a hardware multiplier in the FPGA fabric, I can set this to true, and then multiplication becomes a one-cycle instruction, which means that I can do, amongst others, a square root primitive that is quite fast. Then I have with float, that means that the floating point oriented instruction, which are 5 as far as I remember, are loaded or not. And with up download means I'm talking to microcore with a umbilical link. And with up download means that I can directly up or download data memory. And the up and download is consumes quite a number of gates. It's complex, and so I have the choice to either do without it. So much about constants. Yeah, that I must say. VHDL does not have any construct for conditional compilation. And so the way out is to define constants and then do an if, then, and if around code that may or that should or should not be synthesized or simulated. Then the next thing is crystal frequency, clock frequency. These may be different if I use internal PLLs of the FPGA. So the crystal frequency may actually be smaller than the actual clock frequency. Then cycles, I can run microCore at a clock frequency which is much higher than what is required by the delay times of microCore. So the delay time of microCore in most FPGAs is close to 14 nanoseconds. But if I have a system that requires a higher clock frequency, I can say, okay, one microCore instruction should be so many cycles. So let's say I run my entire design at 40 megahertz for various reasons. Then I can set cycles to 2, and then microCore itself runs at 20 megacycles instead of 40, and then it works again. And then I set the umbilical rate, which is the rate of the umbilical link, which is a UART. So then we have. I tell you, there are lots of knobs and switches that you can tune in the architecture to configure microCore. So we have a data width, for instance, of 32 bits. Now, the data width of microCore is more or less arbitrary. You can set it to any value, so not only to 16 or 32 or 64, but also perhaps to 27 or 18. A justification for these strange numbers is that at some time I figured out the internal block RAMs of FPGAs tend to be 9 bits wide instead of 8. And then I said to myself, why throw away this extra bit? And since a 24-bit computer, I believe, is a good choice for instruments that interact with humans and work with A to Ds and D to As, then 24 bits is sufficient. And 3 extra bits means I have extra guard bits on the 24-bit numbers. With floating point, I can say the exponent widths. Interesting side note, I mean, real programmers don't need floating point, right? They do everything with integers, unless you have to convert the temperature of an NTC resistor to its resistance, in which case, depending on which way you convert, either from resistance to temperature or temperature to resistance, you either need an exponential or logarithmic function to do that. And this was something I didn't want to hack through with integers, so I sat down to do a floating point implementation. And then later on, when the whole code was working, I tried it on different data widths, and interestingly enough, a version with 24 bits and 6 bits exponent width was still stable as far as the NTC conversion was concerned. So it is quite usable for quite a big number range. Then we have another constant, which is the data address width, which is the how many address lines will be maintained. And then there is the cache address width, which means how many of those address bits are internal to the FPGA. So if data address width and cache address width are the same values, then I only have internal memory and no external memory. And if I connect external RAM to the FPGA, then the data address width will be larger than the cache address width. There is a second constant for the actual cache size, because if I set the cache address width, then I assume that the memory is always a power of 2 large, which is not always true. Well, it is true in this case, as you can see from this number. That means hex 1000. But in other cases, it's not true. Then there is a register address width. Well, the registers in microCore are memory mapped, and they are mapped to the high end of memory, which means that I can represent the register addresses by small negative numbers, starting at -1, going down to whatever I need, -10 or so. And so depending on how many registers I have, I can limit the register address width in order to save resources of the FPGA. Then I have numbers that I compute on this level, and you see these strange signs here, dash, tilde. This is again something for the VHDL interpreter in force, and it tells the VH interpreter, skip the following code until this tilde here is found by force, and then it starts interpreting the next constant again, which so these constants here all have to do with external memory. And for instance, it says what is the natural word width of the external memory, and then from this I compute how many accesses I do have to make in order to fill the 32 bits of the data width. And that means that I have sub bits which run faster than my address bits in force. And then I also have the RAM address width. That's not so important here. Then program memory parameters, instruction width, well, always 8. Program address width 13, program size. So this is very similar to what I have done here with the data. And then the last parameter is the boot address width. Depending on how large the the cold boot program is, I can set it to the proper number again in order to save resources. And you see this comment here, must match the size of bootload.vhd, or else the bootloader cannot be synthesized in its full length. Then there's another important parameter, which is the trap width. All the trap vectors, of which reset, interrupt, pause, and a break instruction, which is needed for the single-step debugger, they all reside in the lowest part of memory starting at 0. And trap width means that 2 by the power of 3 means 8. Each trap vector is 8 instructions wide. So if I have a trap that needs less than 8 instructions, it's fine. I can immediately compile those into the trap vector, or else I compile a branch to the actual code. Then we have stacks. We have the task address width set to 3, which means that I will have 8 copies of both the data stack and the return stack. And so I can do rather fast task switching. It takes, if I do a full task switch, that means I execute the pause, I go through the scheduler, I find another task ready to run, and I come to the conclusion, okay, I have to load a new context. That takes 7 microseconds, which I believe is quite a good number. Then there is the data stack address width and a return stack address width. So this defines on how deep my stacks are. And then we have another number, which is the address of the return stack. For speed reasons, I always put the return stack in internal memory of the FPGA. And this here is then the starting address. And I put it at the top end of the internal of the cache data memory, and this is the starting address of the stack area of the return stack area. Because I mean this, I must say, in microCore the return stack is inside the data stack. The reason for this is twofold. For one thing, I wanted to make microCore be able of executing compiled C code. And C is notorious of misusing the return stack for data values and data areas. So this is why it's in the data memory. And the second reason is there is no instruction in microCore that needs access to the return stack and the data memory at the same time. And I believe this is true for all 4 systems. And so this doesn't actually slow down execution, but we have a shared memory here and don't need extra RAM for the return stack. Then we have DSP widths and RSP widths. They are automatically computed from constants I have defined before. I say where the sign bit is. I say how many octets I need to fill the 32-bit data widths. The reason for the octets is that the umbilical link over a UART only transfers bytes, so I have to know how many bytes I have to transfer for one data word. So these are all the constants that set the architecture of microCore. And now we come to internal and memory mapped registers. So the first one is a status register, and these are all the status bits which I need. So carry, overflow, interrupt enable, interrupt in service, literal. I have to say something about interrupt in service. If microCore jumps into the interrupt vector, trap vector, then it sets the interrupt in service bit and thus disables further interrupts. And when I come out of the interrupt routine again. I do an interrupt return, and that restores the status register before jumping to the trap vector. And by this mechanism, the interrupt in service bit is reset to 0 again. So it automatically re-enables interrupts again. The lit bit, I have talked about this briefly last time. The lit bit tells me whether the previous instruction was a literal instruction. Because if the previous instruction already was a literal instruction, then I increase the number that is already on the top of stack. And when the literal instruction is 0, then I push the literal value on the stack, and when it is 1, then I extend it, shift it 7 bits to the left, and concatenate the new literal value. Then we have negative, we have 0. There are 2 bits for division, so I called it the sign of the, this is the sign of the dividend and the sign of the divisor. This is needed because I have single-step division instructions which can be interrupted in between stepping through the division. And so this maintains the sign so that at the end, I still know what I started with, so to speak. And then for floating point, we also have an underflow bit, which can happen by the normalized instruction. Then we have the data stack pointer, we have the return stack pointer, and then comes the flag and interrupt register. I have amalgamated these 2 into 1. So let's start here with the flag register. So this defines it. It has the address -5, and I have a flag DSU that tells me whether whether the umbilical link is actually connected. And this is important for a running microCore system in production, because I can disconnect the umbilical link and let the thing run and let it do whatever it does. And when I want to monitor it or change code or do whatever I want interactively, I can reconnect my umbilical link, and this will eventually set the DSU flag again and restart, and actually it will restart my terminal task that allows me interactive access into microCore. And the nice thing about this technique is my running system is not interrupted. It is still running and continuing to run. The only difference is that it has to maintain the additional terminal task. Then I have a flag which is used as a semaphore. We are talking about the constants for, let's call it, the bare bones microCore, and the semaphore flag and the bit out flag. These are just flags which are used in testing the core integrity and in simulation to be able to test the behavior on semaphores and to use bit out to signal something to the simulator. Then the thing has a version register. As you can see up here, there is a constant version, which is meanwhile at 2342. And so in the running system, the version register will contain 2342. So at any given time, if you connect to microCore interactively, you can find out which version it is currently running. Then there is a debug register. Now this is a register of the umbilical link, which allows to read and write. I mean, read means the host sends something to microCore. Write means the target, microCore, sends something back to the host. And the debug register is the communication medium inside of microCore to do that. And this debug register, as I said before, is supported by an entity in the code that takes care of the umbilical communication without using the processor, because the processor is supposed to do its thing and run ahead. Then there is a timer in the system, the time register, and here I can say how many ticks it should do per millisecond, and usually I set it at 4 ticks per millisecond. That means 250 microseconds. And I am deriving all timing services from this time register. And then we have a control register, which allows me to set and reset individual bits that do something. And here you see the constant, the control bit out, which in the tests is fed back into the flag bit out, and so I can check whether this loop works. So, and then I have another constant, which is min registers, and the highest register number is -9. And if I add more register, application-specific registers, this number grows and grows and grows. And the last large project I had been doing had altogether 31 registers, of which 4 were A to Ds, and the remaining ones were mostly DACs. To set it up in this way, it is very easy and efficient to add a register, because the VHDL code, out of the registers, the VHDL code builds one vector that extends from max registers to min registers. And so if I add a register, I have to add register names here and give it their address and adjust min registers, and that automatically includes it in the VHDL code. Then we come to the various subtypes which I defined for efficiencies and to make the code more readable. Here you see, here we have it. Here you see the data sources. So the data sources are these registers here. And you see it is an array of much registers down to min registers of data bus. And data bus is, in that case, this case, it's 32 bits wide. Another very important resource of microCore is the microCore bus. And this is the definition of the microCore bus and all the signals that are carried by the bus. And I come to this later in the overview of the structure of the VHDL code. In essence, the bus is available in each entity that is inside of the microCore design. And so every microCore design can use these signals. Core signals, I don't go into that. Then there is a data mem port and the program memory port. The record types, this is one of the reasons why I definitely prefer VHDL over Verilog, because Verilog doesn't have that. So in Verilog, you would have to repeat all these signals on each entity again, whereas in microCore, you just hand over microbus and that's it. Okay, then there are command bytes for the umbilical link. And then I have functions in order to couple the access to the internal registers to the force system. And so here I have functions, the definition of which is at the very end of this file. I have functions that will be true, return Boolean, that will be true if I access this register, which is given as an integer, and the same can be done when writing a register. So in the code, at any given moment of the VHDL code, I can make actions depending on whether I do a fetch or a store on an internal register. And that is all the flexibility you need in order to work with the memory map registers. And then there is another guy that I don't want to get into because that has to do with pause. It is the hardware semaphore, which eventually allows you to do all the mutual exclusion and resource sharing in hardware instead of in software. And now come the opcodes, and I have done a grouping of the opcodes, which is more or less arbitrary. You see, it is the bit 7 is always the lit bit. Then I have what I call type. So we have types branch, ALU, memory, or user. And then I have stack, which is none and both, well, because of 0, 0 and 1, 1. And then I have the pop and the push. It does no longer have much to do with decoding of the instructions. It is grown historically, and I still find it useful in order to come up with this table here. And this table now is a very brief overview of which instructions have been defined, and you see there is a lot. I don't want to get into the single instructions now. We can do this later. And then come all the constants of the opcodes. And here you see how I have defined them. So these are all just numbers, the instructions, how do we call this? The opcodes, basically. Okay. So, and you see in microCore, there is quite a number of unused spaces here, especially in the user group, which means there is ample opportunity for application-specific instructions. And the last one I have implemented was an instructions that does a multiply of 3 bytes in a 24-bit data word multiplied with 3 bytes with another 3 bytes. Actually, the instruction is needed because I'm driving several LEDs, red, green, blue LEDs, and the tolerances of these LEDs are just terrible. So if I set the LEDs to the same current in all LEDs, I get anything but white. And also between different LEDs, the color will be different. So this multiplication step instruction is needed to calibrate the LED tolerances. And I can now do this in one instruction. That means in 40 nanoseconds if I have the two numbers on the stack, and that will do it. And it turns out that this instruction is, I think, a 6-liner or so. So it's very simple to do your own instructions. Okay, now we have all the constants. Here is the actual definition of micro register read and micro register write. And at this time in the game, I cannot put any actual numbers here because this is the first file that gets loaded, and it doesn't know anything. But I have already defined the microbus port, and so I can access the microbus access address, the microbus write, the microbus register enable, and the microbus clock enable. I can access this because I have microbus available, and that is the whole mystery why I can define this at such an early stage in the game. And the semaphore bit I leave out for today. So that is the architecture description, which gets interpreted by both the VHDL code and the Force Cross compiler. Any questions so far? That doesn't seem...
I just have a comment. Really nice.
Thank you. So that was the VHDL. Back to the architecture.
I'll make
just
a comment also. This is mind bending. This is a whole. Your head has got concepts and so forth in it that are just whoa. They're off. You know.
Yeah, I'm doing this since 2001, and so I went through a lot of metamorphosis of the entire code, and especially the structure changed a lot. And now I think I'm at a point where I'm very satisfied with the existing structure. So this is now the architecture. It's just the reminder. We have the internal data memory, which shares, which houses the return stack. We have a top of return stack register. We have a top of stack and a next of stack register. Actually, I came to the conclusion I can simplify microcore more in throwing out next of return stack, because I can always read the top of the data stack and write the next data stack. So this is not actually needed, but it's nice because this way I can do step instructions that utilize TOR, TOS, NOS, and the top of the data stack. That means I can use 4 registers at the same time to do things. And that allows me to do a lot of things.
So Klaus, what are you going to do next month? Any idea?
What to do? What next? You mean
next month? I think we have to move on pretty shortly.
Okay. Yeah. Then I will have to delve into the. Let me just. I will not delve into further VHDL code then, but it would still be interesting. So to just recap here. So I talked about the data interface, or actually, I mean, the data width wide thing is this, and the 8-bit instruction, which is this portion of the code. And one of the last changes I did, I have no apparent instruction register. Instead, I have a program memory address register. And if you use FPGAs, you cannot evade them because they are firmly built into the block RAM structure of the FPGA. And unfortunately, you can't read it back. But it's there and it is needed. And if you want to access a program memory or any memory, if you want to do a fetch on the memory, you need 2 cycles. In the first cycle, you have to set the address, and in the second cycle, you can read the result. So that has also ramifications. And here then is a list of memory map registers. We have seen this: status, DSP, RSP, interrupt flags, flags, version register, debug register, timer, and control register. Oh yes, this is something I didn't say, which is important. Talking about the flag register. So
Klaus, can you hear me?
Yeah.
It's to wrap it up. Can you bring it to a close in the next minute or so we can get on with
then I will not tell you how you add interrupts to the design. I just go through the main slides. So this is a VHDL structure. Basically, we have a test bench, of course. We have the top file that connects to the pins of the FPGAs, which I call it FPGA. And it has one entity that is the data cache that contains memory. Then we have another entity, which is the external static RAM. And then we have microCore VHD itself. And the central piece of microCore is microcontrol that does all the all the instruction decoding. And a special entity is microCore arithmetic, which is the add and the multiply. And because on some architectures you have to instantiate IP blocks in order to be fast enough, both for the add as well as for the multiplication. Then there is this whole called bootloader, which is its own entity, and then the program memory. And then there is this large block, the debugger and the UART that connects the umbilical link. So that is basically the structure. And then there is the functions package, which is just a collection of functions which are handy to use in many places. 2-cycle instructions.
Okay,
I cannot talk about this
interrupt you, and as grateful as I am for your content,
okay,
we really got to move on.
Okay, that's it. And thanks for your for looking at it.
Fantastic.
Thank you very much, Klaus.
Very beautiful code.
All right. Without further ado, we'll move on to the April challenge, Bill.
Well, you have to unmute.
Thank you. I'm laughing. Oh, that's good. And thank you for the help. And welcome to all the fourthers there. And thank you for Klaus. This is really, I won't editorialize too much, but this shows what fourth can do if you are intimately involved with applications where you cycle between application, processor design, back and forth, you come up with reality, with what really works and what's really useful. So thank you.
Yeah, that's true. I mean, this is essentially the same thing that Chuck went through when he designed Force. I mean, he did applications and the Force changed with every application, and the same happened to me.
On the other hand, though, you are much closer to applications than Chuck is, because Chuck was often working one level or so above the physical applications, working with other people and filtering in the way. And you are seeing the raw application directly, and you have accountability to the user directly, which is really good. We're doing our challenge today. Well, I'll go into the content of it in just a moment. Do we have any participants who wish to present on the challenge?
I can.
Brad says he is in on the deal, so that is very good. Anyone else to participate on the challenge?
Well, I sort of did a riff on it. I was going to just include that in 5 minutes of my talk, but because it's sort of more at the upper large scale end of things, but I don't know whether I want to include it now.
All right, let's move along on that, and that's good. So first, let's go to Brad, and you have